All right, so let's continue with chapter 15. So we ended on this problem last class, or last lecture, and so we found the KC for situation A, for B, and C. And so as said, we see here we've got a KC of 9, a KC of 1, and a KC of 1/9. So we want to know, what do those numbers mean? Like, is 9 good? Is lower than 1 good? Is 1 good? Like, what does that mean? So let's understand the meaning of the equilibrium constant. So when KC is a lot bigger than 1, so for example, like my 9, this is when the reaction is strongly product favored. So let's think about why. KC is products over reactants. So if I want a number that's bigger than 1 in my KC, that means that this number has to be a bigger number than this number. So you can kind of think about it, like we can plug in numbers. So if products was 10 and reactants were 10, that'd be 1. So if I want it to be bigger than 1, I have to make the products a bigger number. So if products were 100 and reactants were 10, now it would be 10, which is a lot bigger than 1. That would mean I had more products than reactants. So the reaction is strongly product favored, meaning I have very little reactant because it's mostly products. And this is when we see it written as a forward reaction only. So this is when you usually see A plus B goes to C plus D, where it's just one arrow like this. Because most of this is gone and most of the products are formed. And in this case, we can assume it goes to completion. So earlier we were talking about, like, how do I know if it's going to go to completion, or how do I know if it's going to be at equilibrium? How do I know what the situation is? This is how we can kind of determine if we're talking about this chapter or all the other chapters we've talked about before, where we kind of assumed that things went to completion. All right, now let's say KC is a lot smaller than 1. So if KC is a lot smaller than 1, then it's going to be the flip. This is where we're going to have a fraction. So to have a fraction, you have to have more reactants than products. So it would be like saying 10 products, 100 reactants. So that'd be 1/10. Okay? So if I have more reactants than products, this means it's going to be really strongly reactant favored. This means that very little product forms. So I have mostly reactants. I don't really make a lot of products. This is when we wrote no reaction, because it's not actually happening. I'm getting no products really forming, or just a very small amount of products forming. So most of it is just my reactants hanging out. The last situation is where KC is close to 1. It doesn't have to be exactly 1, but it's pretty darn close to 1. So this is where my reactants and my products are going to be at equilibrium. And this is what we're talking about in this chapter. Okay? So we've talked about when it's strongly product favored, pretty much the reactions we did before, where we drew a single arrow. Like all the stuff we did last semester. Strongly reactant favored, we talked about writing no reaction when we tried to see if it was going to make a precipitate or not in our precipitation reactions. Now we're going to talk about if it's at equilibrium. All right, now we went back and we said, when we were on this slide, that it's products over reactants. We said our KC was the products divided by the reactants. This works in general. There is an exception. The thing we have to take into account is, what are the states? Okay, so we have to take into account the states. So let's look at this example. I have CO2 gas, carbon solid, and then 2 carbon monoxide gas. And I want to write the KC. Now here I have gases and solids. Here's the exception. When we write the KC, all pure solids are omitted from my, from my KC value. And I'm going to explain why that's the case on the next slide, okay? So for now, if I say that solids are omitted, then this is how you would write the Kc. Products over reactants. This is a product and it's a gas, so it counts. CO squared. This is a gas, it counts. CO2. This is a 1, so it's just to the first. This is a gas, so I leave it. So that's it. So you could rewrite it if you want, so it's centered. If you're OCD and that bothers you. All right, let's do the next one. I have a solid and a gas. So if I have a solid, that means I don't use it. So Kc is going to be products, SO2 to the first, over O2 to the first. All right, so let's talk about why I don't include solids. So we're doing concentrations in my Kc. The concentration of a solid is constant throughout a reaction. All right, so let's think about why it's constant throughout. So concentration is moles over liters. Another way that I can get moles over liters is I could do the density divided by the molecular weight. Density is grams per volume or mass per volume, so grams per liter, for example. Molecular weight is grams per mole. If you do this, this actually comes out to be mole per liter because this mole's on the bottom, so it flips. This liter's on the bottom, so it flips. So that's why you get them on the opposite sides. The density of a solid doesn't change. Its molecular weight doesn't change. So if I have a pure solid, its concentration doesn't change. Okay? So, for example, the concentration of S8 is going to be constant because my density and my molecular weight are constants. So like I said, the concentration is going to be constant. Okay? So this factor is kind of absorbed into the Kc. This is why we don't write it. We kind of can just ignore it because it's not going to change. Another one that we're going to ignore are pure liquids. So pure liquids are also going to be omitted for the same reason. Their concentrations will not change. Okay? So if it's a solid or if it's a pure liquid, we're not going to write it in our Kc equation. So let's think about this. Water is going to be omitted from the Kc, especially in dilute situations. So if I have a dilute solution, that means it's kind of like watered down Kool-Aid. So think about that. It's going to have a lot of water. There's going to be water in excess because most of everything's going to be aqueous, which means it's in water. And then you're just going to have a bunch of water. So the water is in a large excess. So even if it's part of the reaction, even if it's being consumed or made, the concentration of the water doesn't change that much because there's so much of it that if I just made a little bit more or used a little bit of it, the concentration might change, but the amount it will change is so small that we can just ignore it. So we won't write, if it's pure water, we're going to ignore it, and it's just going to be kind of absorbed, just like the solid. So say we want to write the Kc for this guy. So Kc, it's going to be products over reactants. So here's a product. He is not a solid or a liquid, so he counts. The only things that don't count are solids and liquids, and he's got a 1, so he's to the 1. OH minus is not a solid or a liquid, so he counts. And here's the first, so it's to the first. Water is a liquid, so he doesn't count. NH3 is aqueous, so not a solid or a liquid, so he counts. And to the first, because there's the first. So this is what the Kc would look like, and then we can actually get the number. This number is really, really small. So if it's really, really small, we know what that means. We just go back and say if it's really, really small, then it's strongly reactant favored, which means it's not going to really happen that easily. Okay? Now, like I said before, there are units because this is molarity times molarity divided by molarity. So you might think, okay, this is molarity because there's 2 here, 1 here. But units are customarily omitted. We just want to know what the number is. We honestly, all we want to know is if the number is bigger than 1, equal to 1, or less than 1. We don't really even care what the actual number is itself that much. We just want to know how it relates to everything else. All right, let's practice some more. Best way to practice these, okay? Because the whole chapter is on equilibrium constants. So if you can't write the generic KC for this, it's going to get really complicated if you can't do it, okay? So let's do it again. What is the equilibrium constant for the following? So when it says what is the equilibrium constant, you have to know that that is Kc. So it says what is the equilibrium constant? That's Kc. So I need to write the Kc. Products over reactants. Here's my first product. It's a solid. If it's solid, no go. So then I look at the next one. It's a gas. Okay, I can write it H2O. There's a 2 here, which means it's squared. Next one, it's a gas. Okay, I can write it SiH4. There's a 1 here, so a 1 here. Next one, it's a gas. Okay, O2 squared. That's it. Okay, solids are omitted, gases count. All right, next one, write down Kc. So I gave you the symbol for equilibrium constant here. Kc is equal to aqueous, that counts. So I write it down, Na2SO4. It's to the 1, so it's to the 1. Next one is a liquid. It's water. It's all in aqueous stuff. I don't include my pure water because it's the solvent. Everything's in water, so I ignore it. All right, reactants. This is aqueous, so it counts. So I do my NaOH to the 2 squared, because that's a 2. This is aqueous, so it counts. H2SO4, and I'm done. If it's a liquid or a solid, I don't count it. That's it. Those are our exceptions, okay? So now you know how to write a Kc, period, no matter what it is. Now we can do it. Now, what if I wanted to relate the Kc from one equation to another? Kind of similar to like what we did with our Hess's law. What if I wanted to manipulate an equation to get another equation? We're going to do something similar. So we want to know how the Kc's are related to similar reactions. So let's look at the first one. So here's my reaction. N2 gas, 3H2O gas, 3H2 gas goes to 2NH3 gas. Let's write my Kc for that. Products over reactants, they're all gases. If they're all gases, they all count. NH3 squared, N2, and then H2 cubed. All right, I have my Kc. Now I want to go from this equation to this equation. So what happens? My coefficients change. So what happens is I'm going to change the stoichiometry. So if my stoichiometry changes, this is going to change my Kc. Because remember, my Kc, these exponents are based on my stoichiometry. So if my stoichiometry changes, my Kc has to change. So my new Kc would be NH3, just to the 1, N2 to the half, and H2 to the 3 halves. Now, let's talk about what we did. This new Kc, how does it relate to the original? So how does this guy relate to this guy? Or another way you could think about it, what would I do to my original, what would I do to this one to get this one? Now think about it. So let's just look at the top. I go from NH3 squared to just NH3. So if I want to go to something squared to it by itself, I had to take the square root of the first one to get to this one. So the new Kc is the square root of the original Kc. All right, so here's my rules. You can just write them up here. Here's my rules. 1. If I divide the original equation by 2. So this equation was divided by 2 to get this. My coefficients, 3/2, now 2 over 2 is 1. So if I divide the original equation by 2, the new KC is going to be equal to the square root of the old. So this is the new, this is the original. Okay? So the new KC is going to be equal to the square root of the original KC. Let's look at the second option. The second option is I can multiply. So I can multiply an equation by a factor. So if I multiply the original equation by a number, then I'm going to raise KC to the power of that factor. So my KC new would be the KC original to that factor. So square, cube, whatever. So if I multiply it by a number, which actually if you look here, if I take this and go here, it's the same thing as multiplying by a half. I could take the KC, raise it to a half, which is the same thing as a square root. So actually, if you only know this one actually has this one in it. If you realize that if a number is to the half of something, so if you have like x to the half, that's the same thing as square root of x. If you realize this right here, then you actually get this number 1 within number 2. Or you can just remember them separately, whichever works. All right, so this is similar to what we did with Hess's law. If you manipulate the reaction, you got to change the enthalpy. So if I manipulate the reaction here, it changes the KC. All right, so that's if I divide by something or multiply by something. Now let's talk about if I flip it. So this is the same one we've been doing. NH3 squared N2 H2 Q. Now, what if I reverse my reaction? What if I reversed it? So here, now that 2 NH3s is on this side, the N2 and the H2 is on this side. What if I flip it? Now my KC, still products over reactants. So now it's N2 times H2 cubed over NH3 squared. So if I reverse my reaction, what happened to my KC from this KC to this KC? It flipped. Okay? So if you reverse the reaction, you invert the KC. So if I have the original KC value, to get the new KC number, it's just 1 divided by my original KC. So if I want to get the number, it's just 1 over. All right, last thing. What if I wanted to combine my KC? Just like we did with Hess's law, where we took reactions and we added them together, we combined them together. What if I wanted to combine my KCs? So if a reaction could be written as a bunch of steps. So here's my first step, here's the KC, NO squared. N2 to the first, O to the first. Here's another one, NO2 squared. NO squared O2. And then I want to get to this guy, NO2 squared, N2, and then O2 squared. So to get from these reactions, these steps, to get from these steps to the overall, what we would do is we would just add them, right? If I added them, then this 2NO and this 2NO would cancel. I'd have N2, I'd have 2 of these O2s, and then the NO2. But what do I do to the KCs? I don't just add the KCs. What I do to the KCs is to get my KC overall. What I have to do is I have to do KC step 1 times KC step 2. So let's look at this. I want to get this guy. So I take the first KC, NO2, N2, O2, times the next one, NO2 squared, NO2, 2, O2. If I work this out, you've got an NO squared here and an NO squared here. Now let me change my color. This NO squared and this NO squared canceled. There's nothing for the NO2 to cancel with, so the NO2 is just going to stay where it's at. This N2 is on the bottom, so he stays where it's at. And if you have an O2 times an O2, he's in O2 squared. So to get the new KC, you have to multiply the steps together. So you have to multiply the steps together to get the new KC steps. Okay? All right, so let's look at a problem. We're almost done. Hang in there. If you need to take a break, pause the video. You can always pause it at any time. All right, so let's look at this. It says the following reactions have the indicated equilibrium constants at 100 degrees Celsius. So here's an equation with a KC. Here's another equation with a KC. I want to determine the KC for each one of these reactions. All right, so I'm trying to get A. So I have to manipulate either equation 1 or equation 2 to get my wanted equation, just like we did with Hess's law. So what would I need to do for the first one to get my new one? What do I have to do? So use the first one or the second one, first of all. So let's look. I'm trying to get NO. Who has NO in it? He doesn't have NO. He has NO. Is NO on the correct side? Here he's on the left, here he's on the right. So I need to flip him. So I'm like, okay, I need to flip him. Or you could write it up here, I need to flip him. And then if I flip him, do I have the right number? Yeah, so there's 2 of these, 2 of those. So I need to flip number 1. I need to flip equation 1. So let's just write it right there. So I need to flip equation 1. So if I flip the equation, what do we say my rule was? So let's go back. If I reverse the reaction, then my KC is 1 over the new KC. Okay, so I'm going to flip it. This one's reversed. So KC for equation A is equal to 1 over the KC for number 1. So my KC that I'm trying to find for equation A is 1 over this KC, 0.014. When you do that math, you get 71.43. That's my KC. All I had to do was recognize which one this goes to and how I need to manipulate the original to get the new. All right, let's look at B. I need B. So let's look. I have NOBR. So where's NOBR? NOBR. Here's NOBR. Okay, so I'm going to do something with the first equation. Is NOBR on the same side? Yep. Is it the same number? No. He's 2. He's 4. So what do I need to do to equation 1 to get B? I need to multiply by 2. So I need to multiply by 2. Or let's see, equation 1 needs to be multiplied by 2. Okay, so I need to multiply equation 1 by 2. All right, so if I'm multiplying, let's go back to our rules. We said if we multiply the original equation by a number, then my new KC is the original KC to that number. Okay, so KCB is equal to KC1 to whatever that new number is. That number was 2 because I had to do 2 times 2 to get my 4. Okay, so let's work it out. KCB is equal to the KC squared. And that gives me 1.96 times 10 to the negative 4. Okay, so that's my new KC for B. let's do the last one on the slide. Almost done. Okay, let's erase all that. All right, I need NOBR. This is the only place NOBR is at. This is on the left, this is on the left, so we're good. I want only one NOBR, I have two. So what do I have to do to this first equation to get only one? Yep, I need to divide. So equation 1, divide by 2. So I need to take equation 1 and divide by 2. So let's go back. What do we do? Whoops, too far. What do we do if I'm dividing my original equation by 2? Right here at the top. It says divide the original equation by 2. My new KC is the square root of my old KC. Oop, too far. My new KC doesn't want me to write right there. My new KC is equal to the square root of my old KC. So, erase this. My new KC is the square root of 0.014. So my new KC is gonna be 0.12. All right, almost done. This slide and then we're done for this lecture. So let's look at D. I've got NOBR. NOBR is only in this slide. Cool. Is it on the same side? Yep. Is it the same number? Yep. So do I have to do anything to the first one? No. Well, that seems kind of weird that I don't have to do anything to it. So does this and this match up? Are they the exact same? No. It's got part of it. It's got two NOBRs, two NOBRs, two NOs, two NOs, and that's it. I don't have BR2 anywhere. So I've got to do something else. So what else do I have? I didn't have any Cl2s in that first one, but there's Cl2 here. Oh, I bet I'm gonna have to combine these two equations. So let's look. So I know that I need the NOBR, which is here, and then I don't have to do anything to it. So equation 1 stays the same. Okay, cool. Let's see. So that would give me that guy and would give me this guy. All right, let's see if I need to do anything to equation 2. Equation 2, I need a Cl2. It has a Cl2. I need 2 BrCls. 2 BrCls. So equation 2 stays the same. Now, the only thing that I have left are these BR2s. But they're on opposite sides of the arrow, so they're going to cancel out. So when I add up my reactions together, the BR2s cancel out, and then everything is left the same. So all I need to do is add equation 1 and 2. I don't have to manipulate the equations themselves. I just need to add them together. So let's say, okay, well, how do I do that? What did we say? If we add reactions, then to get my new KC, I have to multiply the steps. All right. So if I want the new KC, that's going to be KC1 times KC2. So to get the new KC, it's going to be 0.014 times 7.2. And that's going to give me 0.10. All right, last one, and then we are done. So I need NO. What has NO? This has NO. Is it on the same side? Nope. So I'm gonna have to reverse it. Is it the same number? This is 2, this is 1. So I need to reverse it, but I also need to divide by 2. All right, so if I flip this, divide by 2, we're good. If I flip the BR2s, I don't have BR2 down here, so hopefully it'll work out. If I flip this, NOBR is going to be on the other side, and I only have 1 if I divide by 2, so that works. All right, now let's look at the other equation, equation 2. I need a BRCL here. This has a BRCL, but is it on the correct side? Nope. So I need to flip it. I need 1. It has 2. So I got to do the same thing. I got to divide by 2. So if I flip it and divide by 2, that's good. This is going to be on the other side, and if I divide by 2, it's a half, which is what I need. And then that gives me everything in my equation, and should everything else work out, here's a BR2, here's a BR2. They're going to flip sides, both of them, and they'll both be divided by 2, so they'll cancel. All right, so now we want to do the math. So let's look at the math. So for equation 1, I have to divide by 2 and reverse. Okay, so let's talk about what that looks like. So if we reverse, that's the 1 over KC, and if I divide by 2, that's the square root. So for equation 1, let's manipulate this number first before I deal with the fact that I'm going to add these equations together. So for equation 1, I need to do 1 over the number and the square root. So that's going to be 1 over 0.014 and square root, which gives me 8.4515. For equation 2, I have to do the exact same thing because I'm reversing, which is 1 over KC, and dividing by 2, which is square root. So I need to do the square root of 1 over KC. 1 over 7.2 gives me 0.3727. Now, all I've done is manipulate each one. I still have to add them together because to get this guy, I added this one and this one, these 2 equations. So what do we do when we add them? Right here, we wrote it before, we multiply. So to get my KC of my final, it's KC for 1 times KC for 2. You want to plug in the numbers after you've manipulated the individual equations. Don't try to do this all in one fatal swoop. 8.4515 times 0.3727. So after you manipulate each equation, now you're going to multiply them together. And your new KC is going to be 3.15. Now, I know that's a lot. If you can do E, that's as hard as it gets. E is the hardest it will get for this type of problem. So if you can just manage to do that one, you're good, okay? So that is it for today. I know this was kind of a long lecture, but we cranked through and we got all the math done for this part, all right? So make sure you work on your homework problems, make sure you're staying up on the rest of your stuff for your other classes, for lab, for a recitation if you have it, and for everything else. Be safe.